Uh, so this section will talk about normal vector to a surface. We know that once you have if you're given surface, right? Given surface in a three-dimensional space, and at the point you can talk about tangent plane, right? So here's the tangent plane is defined to be the space of all tangent vectors. Okay, now what are the tangent vectors? Tangent vectors actually they're coming from the tangent vectors to the curve passing through this point. So there are several curves passing through this point, and we get tangent vector. Okay. So if the surface is this area is covered by regular surface patch, okay, and this is in the UV, okay, this is in the X, Y, Z space. Then the tangent space is spanned by those two vectors, okay, those two tangent vectors, and this is independent of the choice of a particular regular patch, surface patch, okay. If this is a point here, U0, V0, and this is a sigma U0, V0, then I have to put more details here. Okay. Now, if you choose another regular surface patch, then you will get U tilde V tilde. Okay, and for example, here's another one, and this is a tilde, right? And here's U tilde V tilde. Okay, that point is sent to here. Okay, then you will get the same vector space. The reason is those two tangent vectors from another regular surface patch, okay, are actually coming from, can be combined, a linear combination of the sigma U or sigma V. So that's why that is why we have those two vectors span. Doesn't matter which regular surface patch you choose, you end up with the same two-dimensional plane. Okay. Now let's prove this fact. Okay, why this is true. I can define this map by V. Okay, this could be something like that. Okay, right? This is called the transformation between this patch. Okay, so so use a chain rule. Okay, use a chain rule. I'm going to take a look at this, right? Yeah. So this map is going to be here. Let me write down the relationship. Okay, I should write in this. This is a sigma, right? The sigma cube, right? Right. So this is a. Okay, this is a compensation. Okay. So sigma u, when you differentiate, right? Sigma tilde u tilde, and this is a right. Right. So here's another one. Okay. Now here we write as u and v in the form u tilde v tilde. Okay. So therefore, you see that. So the basis, I'm going to express in another form. This is the basis sigma u and the sigma v can be also simply written in the form. Okay, and this is actually this is a Jacobi. Okay, so this is also denoted as a Jacobi of the so-called. This is a yeah. So clearly, if in linear algebra, if you have this is a base, here's another base, right? For the vector space, it's a combined. They're related by this in this form, multiplied by matrix and definitely, yeah, and this is invertible, right? And so this from linear algebra, this you can show that the vector space, the vector space spanned by those two vectors will be the same as the vector space spanned by those two vectors. Okay. And that's the proof. So the tangent vector, the tangent space is independent of the particular choice of regular surface space. Right? So the tangent space, tangent plane, usually in dimension 2, it's called tangent plane at the point P, right? TPS is independent of the choice of a particular regular surface patch. Okay. So what is a normal vector? Definition of normal vector. They see once they have a surface, right, and they have tangent plane, so it's two-dimensional. But then for each, this is a two-dimensional plane, right? Right? TPS, right? So for a plane, there's two vectors, okay, and unit vectors are perpendicular to the plane, okay? There are two unique unit vectors n plus minus, okay, perpendicular to TPS, and they are called normal vectors, right? Normal vectors to the plane, to the surface, okay? They're all called normal vectors to the surface at the point of P, okay? So you have two. One, right now we call it, one is called the positive or negative, but we don't know which side is positive. For a surface, we don't know whether there's which side is positive, right? It's hard to tell which side is positive, but there's two vectors perpendicular to tangent plane. Now, how to find it? Okay? How to find it? Well, you can find it in the following way. Okay, let's see. For regular patch, right? There is a gamma here, sigma. Okay, I still use this. Okay, okay. And then I have two vectors, sigma u and sigma v. So the cross product is a vector perpendicular to the plane. Okay, if you normalize it, right? So that sigma u to R3 be a regular surface patch. Okay. Okay. What is this? Okay. So now from the picture you can see that, right? So sigma u okay, this will be perpendicular to the point. So we can use that to get one of the normal vectors, right? So therefore n, okay, n at the point P defined to be normalize it, right? Okay, is a normal vector. Okay, this normal vector is determined by sigma, okay, determined by this surface. So then you will think maybe do you so if there's another regular surface patch, right? And are we going to get the same one or not? That's a good question because there's possibly two normal vectors there, right? So if there's another one, we just did it, right? This is sigma tilde from u tilde, right? And this is the point P, it's sigma from u, okay? This is the surface. So let's see what we get, okay? I needed to write this again, okay? So the map here is from this phi, right? So phi uv is going to be u tilde v tilde, and this is a phi is defined to be okay, yeah, and again, right? So this is sigma is going to be sigma tilde, right? Yes. Okay, then we have this. So let me still recall this. Okay, so for simplicity, I don't want to keep writing u0 v0. Okay, but this is another one. Means you have sigma v naught is p. Okay, but I'm not going to keep writing u naught v naught here. Okay, so remember. This is a u tilde. Yeah, I have to rewrite this again. Okay, we have time, right? Okay. Right, this will be the derivative with respect to v. Okay, I'm going to take a look at the cross product. Okay, the cross product, as you see, this time that, right? And this time that. So this time this is going to be 0. So you will get u v tilde, u v tilde, and v. Okay, that's the first part. Then yeah, then this will be this. I think I can say have another term. this will be V. Okay, that's U too. Right? Okay, so this time that, and this time that. So, okay, there's my file. Any fun? Okay. But yeah, so basically it's two, okay, cross product. So I'm going to switch the order of these two. So I get minus right. So minus okay. So what is this? This is actually the determinant of the matches we got here over there. So let's go back. See, this is actually the determinant of this matrix. Okay. So this is called the Jacobian of the field. Jacobian. Okay. So a U tilde V tilde and a UV and yeah. Okay. So this is a yeah. This is actually just a determinant of Jacobian. All right, so now it's clear if the Jacobian is negative, then what you get here is see, if you use okay, and you're trying to compare this, depends on the sign, right? Depends on the sign. Yeah, this epsilon, this depends on is going to be the sign of the determinant. Okay. Okay, so different students use a different regular surface patch. Maybe you get different norm factor, but there's only two options in class norm. Okay. 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 So what you can do, right? Well, so let's think about what does this mean. So this is actually, okay, this actually is the same surface, okay? For example, for the sigma, it goes like this, and this sigma U, sigma V, okay, it's the same point. But if it's, if the determinant of this is going to be negative, okay? So this is not going to be, okay, that's my file. Okay. So if, well, let me draw the picture again. Okay. So this is a point. Jesus. So my file something's wrong. Okay. Okay, let's wait for it. I just want to explain what's going on when the determinant of the Jacobian is negative. Okay, if if the determinant of Jacobian is negative, what is that geometry meaning? Okay, so this is surface, right? And this is a how about this? I'm going to restart my computer, okay, relog in, okay? This sounds like the software does not work, okay? And I will continue, so I have two files. Yeah, there's no way I can continue here.